So let's welcome Frederic Peschanski. He's a professional researcher, professor at Sorbonne, which he told me, yes. UPMC merged with Sorbonne in January. He's a theoretical computer scientist, and he will talk about generating random structured data, which is important for testing, performance testing. I think everyone's done it, just generate a data structure, and he will tell us how to do it fast and efficient using Boltzmann sampling. So please give a warm welcoming applause to Frederic Peschanski.
Okay, so let's start. I will maybe make this a bit closer. So it will be an interactive presentation. So I use the wonderful Clips system to do the slide in the browser. If you want to play, maybe after the presentation with the slides, you can do it. And there is also a repository where I explain a little bit how you can do your own talks with Clips. It's a very nice. So maybe that's the main takeaway of my talk. So maybe to add just to the presentation, I'm also and mostly here because I program in Lisp. I would say next year will be 20 years of Lisp programming for me, and I'm so happy that Clojure makes so that I can talk about Lisp programming with other people. I have also a warning. The whole source code of the random generator is in the slides, so I will have to skip some parts of the code. But then you can play with the code if you're interested later on. Okay, so what we want to do is to generate. So I will generate trees, and if possible, large trees. And for this, we need a random source, so a source of random information. So it could be a random bit, just one bit, but it's more practical, at least at the software level, to use a number generator. So it's not so easy to find a good random generator, portable random generator for Clojure and Clojure script, but there is one, and you can find one in test.check. So if you need a good random generator, I recommend a test.check. And the random source we will use is just the generation of a floating point number between 0 and 1. And I need an immutable source, which means I will start with an initial random source with a make random function with some seed. And if you don't provide a seed, it will choose one non-deterministically. And then I will always return an object that I want to generate. So here it's a double number, thanks to test.check, and the next state of the random source. So you can reproduce your generation, and that's very important. Okay, so that's the starting point. But we don't want to generate numbers, we want to generate trees. So we want to generate trees because we need more trees. But for me, it's also to maybe show you that there is an interesting, it's really an interesting case study for random generation when you want to generate proper random generation. I will explain this. And it's also because I love the theory, and I think the algorithms are very beautiful. And I think Clojure is a very good way of hopefully convey this beauty. So how can you generate trees? First, you can use spec and test.check. So I will first use test.check to generate trees. And then if you go to more the science stuff, you will find various algorithms. Some specific algorithms, for example, for binary trees and general trees. And in fact, I did not know exactly what to present at clojureD, so I started with binary trees and general trees. So there is an alternative presentation if you're interested about this. It's a different kind of algorithms, also very interesting. But I will present Boltzmann sampling. And Boltzmann sampling is interesting because it's incredibly efficient and generic. You can generate any kind of trees with Boltzmann sampling. But let's start with spec. So if you use spec, you can very easily specify tree structures. So here I took the simplest one, binary trees. So binary tree is either the tip of the tree, the end of the tree, of the tree. So I will represent it with a nil value. Or it's an internal node, and it's at least a triple of some label. It will be an integer, and a left subtree, a binary tree, and a right subtree, a binary tree. So it's very easy, thanks to spec. And this is an example of a tree. So when I teach programming, that's the kind of tree for students, it's not easy to see that it's a tree, but it's our trees. And you can generate trees using spec, and in fact test.check, with, for example, exercise. So here I generate a small tree, and let's evaluate again. It's a bigger tree, and it has the correct structure, etc., etc. So you can generate trees like this. But I will make two observations. First, most likely the generation is non-uniform. So the number generator is uniform. I will explain this in detail. But for trees, I think it's not. You don't have uniformity. And especially, I don't have any control parameter for the size of the tree. For example, if I want a bigger tree, I can only hope that exercise will give me a bigger tree. So there is no control. If you look into a test-check, test-check has more control for the generator, and of course you can use them from spec. But there is direct support for recursive structures, such as trees, with the recursive generator. So the same spec can be written directly as a generator. And here the parameter should be the size, not of the tree, but of the example which is generated. And if I call it multiple times, you can see that it will generate various trees of various sizes. And so I have two observations to make, which are exactly the same. It's non-uniform, because it's a very simple generation principle. And most trees are small. For example, if I ask for a bigger tree, it won't be really bigger. I think the integer will be bigger. But then you say maybe if I put a Boolean, it will be bigger, but in fact, it won't be bigger on average, right? So the control parameter exists, but at least for the tree structure, it's not really taken into account. So we'll try to do a specific generator for trees. And we will try to make it uniform. So I will explain uniformity. So uniformity is defined for what is called a combinatorial class. It's combinatorics. And I give a very simple example. You take the integer in interval 1 to 100. That's an example of a combinatorial class because it satisfies two conditions. The first condition is that each object of your class must be of finite size. And that's the case if you consider each integer to be of size 1. It's easy. And the second constraint, it's a little bit more complex. If you take all the objects of a given size, the number of this object should be also finite. So for example, here I have 100 integer of size 1. So it's a combinatorial class. And then the uniform distribution is just when you generate a number, for example, uniformly at random, the probability of generating this this object should be 1 to the number of objects of the same size. So for example, 1% chance of generating an integer in range 1 to 100. So uniformity seems really natural when we speak about number, but when we speak about something else than the number, it seems that we are not so, let's say, rigorous about uniformity. And I think that uniformity is important when you generate a structure as a starting point. So I will introduce you to a DSL because we want a generic generator. And this is the spec of the DSL, but I will just show you the example. So it's a really user-unfriendly DSL, but it will work. So if I take the binary tree would be either a tip or a node, like before. And so this plus sign is a disjoint sum in let's say, set theory. And a node, for example, is a triple of, so Z will explains that the size of the node is 1. And I have a left subtree and a right subtree. And so the times operator here is the product, and it's called Cartesian product in mathematics. And then a tip should be empty. So the 1 means empty, and the reason it's 1 is because there is only one object that is empty by definition. And I put it in a product to have something generated when I want a tip, the nil value in a way. So that's a trick of my awful DSL, but it will work. So that's important. Okay, you can create other grammar. So for example, this is a grammar for something like general trees, where you have a sequence of subtrees. But I will take this one as a let's say, more complex example. So it's something impronounceable, a 1, 2, 3 tree, which is either a 1 or 2 or 3. And the 1 is just a leaf of size 1. So Z means size 1. Also, I'm French, so Z is Z, not Z, or I don't know. So it's Z. I will say Z a lot of times. So here I have the Z times Z, so Z to the power 2. And it means that the node here will be of size 2. And the ternary node with 3 subtrees will be of size 3. So the power of Z is the size you want for each constructor. Really, it's not user-friendly, right? But this is the kind of tree we will generate ultimately. Why I use plus times Z in my DSL? It's because it's a grammar for generating tree, but it's also an equation. And I think that's the beauty here, is that I take a grammar, and in fact, it's an equation. So if I simplify, for binary tree, it looks like this. It's an equation of degree 2. You remember equation of degree 2, so we will solve it now. No, I won't solve it. But that's the recursive equation for a binary tree. And we will use this equation to solve our problem of generation. So the first part of the solution is to be able to evaluate this equation. So if I give a value of Z, give me a value of the equation. The problem is that it's recursive. To compute B3 Z, I need B3 Z. And so we'll do it incrementally. We'll take a previous value of the equation to compute the next value, and we hope it will converge at some point. And so as a closure code, it's very easy. The evaluation of 1, the empty object, is 1. The value of Z is Z. The value of plus is plus. The value of product times, it's time. So it's really, you take the equation literally. And so there is an example, Z times B3 times B3 for Z equals 0.25, and B3 equals 2 will be 1. Yeah. No demo effect, it works. So it's very easy to evaluate, and I can evaluate the grammar, which means each key of the map, the non-terminal, will have a value. So that's the starting point. You take the grammar and you take it as a numerical system. And then you continue. Sorry for the vertical scrolling. So now, Boltzmann sampling. So Boltzmann sampling, you want to generate some object, described, so a tree, described by an expression, a grammar, ultimately, and some parameter Z, which is a real number. Could be a complex number, but it's a real number here. If your expression, the tree you want to generate should be the empty object, you return the empty object. If it's a Z, you have to say that you will generate something we call an atom, but let's say an object, and the size of this object should be 1. So Z is just the indicator of the size of the object. So, and the heart of the algorithm is disjoint sum. So to generate either A or B, you will first compute your probability, which is the evaluation of the left operand, the A, in Z. So I have always this parameter available, and you divide by the evaluation of B. It will give you a probability, so a number between 0 and 1. And if you are below, so you will draw a random number between 0 and 1. And if you're below this division, you will generate an object of type A, and otherwise generate an object of type B. So that's Boltzmann sampling. And for product, it's just if you have 2 operands, you generate a pair. If you have 3 operands, you generate a triple, etc., etc. So there is no random generation for product. Only the disjoint sum is probabilistic. And if you follow these rules, you have a guarantee that the sampling is uniform. So you don't know the size of the object because your parameter is not the size, it's a real number. But if you generate something thanks to this number and this expression, you will have an object, and this object will be uniform, which means the probability of having this object is 1 to the number of the object of the same size. But you don't know the size. So the problem is our control parameter in the Boltzmann sampling. How do you control this parameter? So what should be the value of Z in the algorithm? And also, there is some computation to do. You have to remember it's iterative, it's recursive, let's say. And so I will show you a very nice pre-computation where all the probabilities are computed before you start to generate the tree. So let's go into the details. So for the choice of Z, we will use something called singular sampling. I will talk about singularity, the next version of ourselves. No, it will be a simpler version. So if you look at the math, the equation I gave you can be we can prove that they converge if you take Z equals 0. So you evaluate with Z equals 0, and you compute incrementally until some precision is reached, and then it will converge, no divergence in 0. Moreover, there is one point between 0 and 1 where it will stop converging. So it converges in 0 and then until some number called singularity. And when you reach the singularity, it will diverge. And so singularity is the limit of the convergence process. And there is a theorem, very interesting theorem, that says that if you take the singularity as the parameter, the expected size of the object you will generate with this algorithm is infinite. So if I want large trees, it's a good starting point. Infinity, it's quite large. And so we will do that. So the first question is how to find the singularity, and we'll just use the numerical system I explained to you. So I won't go into the detail, but let me try to find the singularity for binary tree. Binary tree is a special case because you can solve the system symbolically. It's an order 2 equation. And the result I can give you, it's 0.25. So let's see if we find 0.25. And I explain the process of this small algorithm. You know that the convergence is between 0 and 1. So this is your starting interval. Then you take the point in the middle, so it's a typical dichotomy, and you try to evaluate your system, as I explained before. And here you will see that it will diverge in 0.5. So you know that it will be between 0 and 0.5, and so you will take 0.25. Yeah, that's the correct solution at the end. And then it converges. Okay, so I have some numbers at the end with this evaluation, and then I will try to the algorithm will try to refine, because the algorithm is not as intelligent as I am, because I know I can stop here. So I will continue, for example, 0.3, etc., and it will always diverge, and we can prove that it always diverges. So when you reach some level of precision you give to the algorithm, you will only keep the 0.25 value. So you have the singularity and the evaluation of the grammar at this point. And of course, you can do it with other grammar, for example, or a more complex grammar. Here, you cannot solve the problem symbolically, I think, or maybe it's possible, but it's advanced mathematics, we'll say. But numerically, it's quite easy. This is the singularity for this system. It's not exact, like 0.25 or something like that. Okay, so we have a process that gives us the singularity. There is one function that so I did not give the detail. There is one function that is interesting inside this oracle, the previous function. It's called Newton iteration, and I won't describe Newton iteration because you have to know what is Newton iteration. And why you do have to know that? It's because you have to read SICP, or you already read SICP, because it's in the first section of SICP. Maybe it's not the simplest example, but at least, so that's exactly what is explained in the SICP. So I won't describe. The other thing I won't describe is here. So it's just a very simple Clojure code, very easy to read, but we won't read it. I will explain to you how it works. So that's the pre-computation part. I explained that either you compute probabilities when you generate the object, or you can see, and it's quite easy to see it, that you can pre-compute the probabilities. And that's just the pre-computation part. I will show you how it works. So I start with this grammar here, so my strange trees. And the decorated version is this one. And what it did, it's very simply, it's to pre-compute the probability. So for example, to generate a tree, I have 3 choices. And what I will do, I will generate a random number between 0 and 1. If it's below this value, this one, I will generate a 1 tree. Otherwise, if it's between this one and this one, it will generate a binary node. Otherwise, with probability 1, you will generate a ternary node. And this is the correct, these are the correct probabilities for Boltzmann sampling with this grammar. And so we have a very nice pre-computation here. And okay, so the algorithm I explained is just very easy to write in Clojure. So it's the choose, so I take a random source. Here I have 50% chance of having one node. So it will occur quite often. If I say 10%, it will occur less. It occurs less, so it seems to work. But really, Clojure is a very nice language to describe algorithms because this is beautiful code, I think. I'm very proud of having wrote like this. No, it's really a very good algorithmic language, I think. So now we can generate trees. So that's the heart of Boltzmann generation. So that's exactly the pseudocode I explained. If it's a 1, you generate, so nil will be, let's say, empty. And Z, I will generate an indicator that Z must be generated. And then plus is choosing a branch, as I explained. And the product is generating a product, tuple. But you have to always propagate the random source. So it's reduced in a way. Some people will say it's a state monad, but you don't need to. A pair is enough. So it seems to work. It generates a tree. This tree is uniform. It's always the same. Oh, it's a small one. No, it doesn't work. No, there is a problem. Okay, so we cancel the no. It doesn't work because I don't have any control. Oh, this one is, no, it's not very big. No, it doesn't work. The reason it doesn't work is that your control parameter is Z. And if you look at Boltzmann sampling, you don't select the size of the tree. You only have this Z. So the size will depend on the random generator itself. And the problem is that the distribution of the sizes, not the objects, but the size of the object, is maybe on the camera, it's like this, which means that there is a very high probability that you will generate very small trees and a very small probability of having infinite trees. And so you have to work to control the size. And to control the size, the first step will be, instead of building the tree, it will be faster and more memory efficient just to compute the size. So this is just like the generator for tree, but it just computes the size. For example, if the size is the empty object, I just propagate the size. It's the same size at the next step. If it's an atom of size 1, I need to increment the size, because now I have a tail recursive generation of size. So it's very, very efficient, and so I can use it. So I generate the size. So it generates small, not so small, but small size, many small size. So we have the same problem. So we have to generate a lot of numbers to have a bigger tree. So what do? We do a lazy seq. So this is a lazy sequence of sizes. So for example, I will take 20 sizes of trees between 0 and 1,000. You need to put a maximum size because some trees may be very, 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 very large, and we don't have time to wait for them. So you need to filter out so here I'm looking for trees less than 1,000 nodes, and you can see that there are many 1s and 4s and things like that. So the next thing is called, so if you do science, you say, I do rejection sampling. No, it's just filter. You just filter, for example, trees that are less than 100, for example, so I will not have this 1 anymore. So it takes time, a little bit more time. But now I can target trees between 100 and 1,000. I can make this bigger, but the more I get closer to 1,000, the less the algorithm will be efficient. So Boltzmann sampling is about fixing an interval of size. That's already good for control parameter. So these are the size of the tree I would generate in order for trees between 100 and 1,000. I don't have a seed, so I could not find back my trees if I don't propagate the seed. This has to be... So we are at the end, and I have a few more minutes. That's good. This is the Boltzmann Sampler, but no, it doesn't work. I don't know if you see why it doesn't work. Because it doesn't work because I want to generate trees with millions of trees and millions of nodes, and I cannot do that. I cannot do that because I have a non-tail recursive function. So gen3 was recursive, and so it can only generate trees with some depth of a few thousand, which is not too bad. But you need a clojure katas, right? So I propose one clojure kata. You take gen3 and the recursive version, and you write the tail recursive version, and you will obtain beautiful code. No, it's awful. So that's my take on. So I spend a lot of time doing this version, but it's a good clojure kata for tail recursion. Now I can show you the Boltzmann algorithm. So let's generate our strange trees. So here I'm targeting a tree of size 9. Since it's a small tree, it will appear with a very high probability, so I can have a very small interval of size 1. So my tree will be of size 9. And so the tree is of size 9, and I can count the size. It's 3 plus 2 plus 1 plus 1 plus 1 plus 1. It's 9. And so you see the structure is quite constrained. So what we are generating is, let's say, a tree decomposition of the number 9 with 1, 2, and 3. And it's uniform, and there are a few solutions like this, all decomposition. But in my presentation, I said large trees, so let's do some larger trees. So for example, this is the kind of tree. So this one will be uniform, and you can make bigger trees. Or this one should work also. It takes more time, but it's still quite efficient. So you have so we'll start to count. So 3 plus 2 plus, and of course it's a generate generator. So let's try with some other grammar. For example, binary trees. And this is a binary tree, and it's uniform for binary trees. Okay, and a general tree. If you want a general tree, I give you a general tree. Do you want a general tree? Yes, at least 1% of the generator give you. But you keep it for you. Oh, it's only 11. It's not. We'll try another one. No, so it's a kind of general tree. So a general tree has forest inside. Okay, so we have a generic generator. It's time to wrap up. So let's say that I find random generation in general and tree generation in particular quite beautiful if you look at the science and also when you program, because the algorithms are not so complex. Maybe one takeaway would be to maybe more careful about the quality of the objects that are generated. I think the bias should be intentional when you should start with uniform generation if possible, and which means that in a way better automated testing is possible, I think. And okay, so there is other algorithms very interesting in practice for this kind of problem. And if you are interested in the science, one of the best scientific paper I've read is this one. It's a very so it's a little bit technical, but not so difficult, and quite interesting, I think. And thank you.
Thank you, Frederic. Any questions? We may have 5 minutes.
Hello. My background is computer graphics, and of course, rejection sampling we do a lot, but it's not so efficient if you have big rooms. So I ask you if you have looked into other heuristics or stratified sampling methods.
Yeah, maybe to put it in context, even when you use a spec, in general, when you have first the structure of the spec that describes the structure, and then some semantic constraint, like the tree should be balanced or something like that. And rejection sampling means you will just first generate the structure and then filter out, and so it's in general not efficient. Most of the time you won't have any. But in Boltzmann sampling, what is interesting is that you will achieve linear time complexity with rejection. So in this particular case, it works very well. It depends on the interval, of course. So you have to be linear. There is some constraint, but rejection sampling works very well in this case. But after that, it depends really on the kind of structure you want to generate. Like balanced tree is a little bit difficult. Even with this generator, the tree won't be balanced, for example. So it's not a very good general principle, rejection sampling, I think. Yeah.
Very long walk there. Going back to your code.
Yeah, it's ugly.
You're using Java random splittable object.
Yeah, in test.
But this is clips, so how are you managing to get Java rather than JavaScript?
Yeah, I understand. It's a good question. I use the test.check generator, so
they've done all the work for you, basically.
The random namespace, in the random namespace of test.check, you have a generator, and so it uses the splittable random generator of Java. And for ClojureScript, they re-implemented a split algorithm. So you have a portable, but of course it's not really portable. In a way, you will have different numbers, but still you can use it in ClojureScript and Clojure. That's what I was looking for, and I was afraid not to find a good library for this. Test.check is good, really.
Excellent, thanks.
Maybe one last question. Rambo, das aus, wer zuerst war.
Hi, so a double question, but one part is just very tiny, so I hope that's fine. So the first part is, have you packaged this as a library? And the second part is, have you experimented with generating label structures, like with exponential generating functions? They also have methods for that, right? And so I'm just curious if that's worked out as well.
So the first question, no, I'm not in the state yet to create a good library. And one reason, and I think the best starting point won't be Boltzmann, to be frank, will be what is called the recursive method. Because then you can target a size, very precise size. You cannot generate very large, I need for my work very large trees. But recursive method will give you smaller trees. But more so there is, for a library, I think, and maybe I could try to start it, but we should investigate more recursive method. But I think it would be good to have let's say, or to make test check better for tree structure, for example. It could be a good starting point. And the second question I forgot.
Oh,
about EGF, exponential generating function. So, for example, if you want to generate other kind of constraints on your trees, like a balance or something like that, sometimes you have to use EGF to do that. And so there is it's called label structure. So there is a Boltzmann sampling for label structure also. So yeah, it's possible, but
yeah. Well, so I'm just wondering if experimented with an implementation, if it turned out.
No, not in Clojure, not with the Clojure programming language.
Okay, but outside Clojure?
Sorry, Camel, there is some more.
Okay, cool, thanks.
So thank you.